I don't think I've ever said, and now for somebody who needs no introduction. And yet, here we are.
I guess that's because I've introduced myself enough at this point. I just want to add something that was fantastic, Dave. And one of the things, if you saw me working on my phone while you were talking, basically when he gave the whole population density curve, I immediately went in and said, what's the population density of Calvert County, Maryland? Because I know how they vote. Sure enough, it came up 443. I was like, yes, predictive, always good stuff. So I'm just going to talk about the state of commercial quantum, and hopefully I'm not going to be explaining quantum computing to you for the third time, which is also why I was very happy to give David's questions to my time, because we really don't need it. So first off, just a quick review of what quantum computing is. This is the description that I like the best. You can basically claim there are many fathers of quantum computing. David Deutsch is one of about 3. But I like his description of the first technology that allows useful tasks to be performed in collaboration between parallel universes. That's not strictly accurate, but it's accurate-ish. And it gives you a sense of, gosh, if I could look at all sorts of different things, all sorts of possible scenarios at once, how could I solve problems that I can't solve today? And the one thing I want to highlight, just to make a connection again to David's talk, is you can do things like policy hardening with quantum computing, where you can sort of say, okay, I have a policy towards engaging with other countries. If I tweak it here and make another tweak here and make another tweak here, give me all of the policy, show me all of the policy tweaks that result in not war or something like that. And that's the kind of problem we wouldn't even think about solving today because we just don't have the tools for it with our very deterministic computer algorithms. So that's the way to kind of think about it. It's a useful metaphor for quantum computing. You've seen this. I was very happy when I went back and looked at my slides after looking at the presentations thus far that everything continues to be correct, so I got it right. Yay me. And the whole states being envisioned as probabilistic is kind of the big thing that you picked up from the previous 2 presentations, and that observing a particle state can change it, which makes it quite fantastic for cryptography applications. Qubits, there are many more. There are more than that are just here. But just to highlight, one of the things to understand is that the people who are building quantum computers have a choice of technologies. So basically, if you're a useful filter when you're reading about the latest and greatest whatever got discovered in quantum computing is what kind of qubits are they using. I want to highlight the defect-based is actually diamonds. That's why there's like a little pretty image of diamonds. Ion trap, and we can go through what all of these are. You can look them up. Photonic has gotten a lot of attention. Quantum dots, we heard about those as actually their use in solar energy. They're also useful for qubits, and topological qubits are actually very interesting because they're sort of abstract layers of qubits on top of qubits. The main point here is each of these has benefits and drawbacks, and in fact, we talk about that. If you haven't had a chance to look at the technology area benchmark that's in front of you, we talk about that at a little length. The purpose of these are things that we promised you back in March of this year, and we're now beginning to deliver. These are essentially indices, a finger to the wind, how have things changed? So we picked a handful, roughly 30 organizations to benchmark, to look at what they've been doing in the 3 months. Every 3 months they come out. Jim is a little annoyed because we didn't pick RPI, which is one of the leaders in quantum computing, and we really
We are only school in the world which has
as a
quantum machine on campus.
From IBM. And so our problem was we already had IBM, which was saying our big thing that we did was put a quantum computer on RPI, and then we're covering it again with RPI. So I also figured I figured Jim would forgive me. So if you're looking in the list and you're going, why isn't my favorite company, university on here? Honestly, this was supposed to be sort of representative. It's like the Dow Jones Industrial Average. This is not everybody in that is a public company. It's just sort of okay, let's pick a handful and see what they do. We reserve the right to kick people off the list and add people to the list if they're not doing enough or there's a lot happening somewhere else. I think I read somewhere that there's something like 365 or 335 quantum computing startups. Obviously, we've got 30 organizations, of which less than half are startups, so clearly it's not covering the universe, but we do include things like little definitions of stuff like qubits and whatnot. So let's talk about what commercial quantum is. You've heard this before. There's quantum computing. We'll talk about that in this presentation. There's also quantum cryptography. We'll talk about what that isn't in just a second. Quantum sensing. Thank you very much to the clients, you know who you are, who said, yeah, can you please do quantum sensing next because we're really interested in it? So we are, because we are doing tabs in each of these areas, and then there's quantum networking. So we'll talk a little bit about quantum sensing and why we think it's so incredibly important, even though right now it's completely different from quantum computing. This data comes from our emerging technology research study. Some of you were interviewed as part of this study. We asked you questions like, hey, are you doing anything in quantum computing? Do you have a team? Are you using products? Do you have a budget? That's always the kicker. If you have we have a maturity model that's pretty straightforward. If you've got a team, you've got a budget, you're using products, and you have a plan, you probably are more mature than somebody that doesn't have any of those things, kind of very, very high level. Using or evaluating, I kind of lied here a little bit because we did slot everybody's answer into either they're using right now today as of the moment that we're talking to them, they plan to use by the end of 2025, or they're evaluating. It turns out that either they had something going on or they had evaluating, which is like the loosest possible level of using. So by throwing them in the same bucket, the numbers got bigger. It's worth noting, though, that roughly a third of people are looking at quantum computing, a quarter of people are looking at quantum networking. Quantum cryptography, a lot of people said they were doing something there, but let's talk about what it was they were doing. Quantum sensing, there was a colossal, but it's actually quite interesting. So this is our data, primary research, warts and all. Let's talk about quantum computing. This is, and you'll see this little radar chart. The yellow stuff is relatively early stage for an emerging technology. And what we mean is, if you look at that table and you say, oh, here's an organization, here's what they're doing, here's the technology they're most focusing on, what is the big announcement they've had in the past 3 months? If the announcement was, hey, we got funding, or hey, we got a grant, or hey, we formed a partnership, we have a coalition, or we're a startup, we started up, or hey, we just got new people on our advisory board, or hey, and as we'll talk about in just a second, oh, hey, we just discovered some fundamental truths about quantum computing that are kind of important. All of that is very early stage. And as you can see from the radar chart, most of the announcements were in the core research technology breakthrough area, so this stuff is still very much emerging. However, there were announcements around revenue or financial information or customer acquisition, as in somebody paid me money to do quantum computing. Now, as was pointed out by one of the previous presentations, we're not entirely sure that what they were doing was quantum computing if they bought it through the cloud. Jim, on the other hand, well, you can't because it's a black box. They won't let you into it, right?
Yeah, but we've run the computation.
Yes, but and that is actually, yeah, I kind of want, what, a big company would lie about what it's offering? Be still my heart. So basically, if you look at this, if you keep looking at this, you will expect to see those announcements change over time. Obviously, some of this is because the 1 quarter time period, the 1 quarter of the year, 3 months, is a little bit arbitrary, and for a small number in the index, it's going to be kind of jerky, but we'll get to see as the announcements start to move into the green, we can be tracking the increase in maturity. Well, yay. So here are a handful of things people say, well, if there were commercial quantum computing, there is commercial quantum computing. There you go. There's a bunch of companies. There's a bunch more, as I said, there's a couple hundred of them. These are the ones that get most of the press. Some of them are actually public, which is absolutely scary and really a bad idea, I would say, because they are too small to be public, as you can see from their employee count. I just sort of gave you some of the locations. We sort of wanted to look across across the globe. We tried to get representative companies from all over. I will highlight something. We didn't do it this quarter, but we might do it for the next quarters. One of the big differences with quantum computing is within the US, most of the funding is venture capitalists. Outside the US, most of the funding is governments. And that's important because remember how much of this is still core breakthroughs. So I would argue that the US is actually at a disadvantage because we're racing to commercialize something that hasn't actually been developed yet. And we're kind of screwing up. And that's a problem because I can't remember who asked the question, is AI sucking all the oxygen out of the room when it comes to quantum? And the answer is no, because governments are arguably longer range thinkers than private equity folks and venture capitalists. And so you see that the governments outside the US are making their bets and logically organizing things and putting together coalitions and groups and things like that. And here in the US, it's sort of like squirrel, AI, quantum, and we're seeing that happen. And I think that's a problem and something that those of us who are involved in policy should be aware of, I would say. Okay. What are quantum advantage problems? Back in Montreal, I actually did a presentation on those. Some of you may remember them. A couple things we heard some people talking about this, whether they're NP complete, NP hard. I would like to highlight that as of last month, we absolutely conclusively know that many-body problems are in fact quantum advantage problems, which is fantastic. Because many-body problems are like when you're a kid and you're sitting there and you're going, look at that wave. I wish I knew why that wave is going exactly that way and why is that little spot of foam going there and nowhere else. And if I could just model every single, well, at least this is what I thought anyway, if I could model every single molecule of water and understand all the forces on it, I would be able to predict exactly what happens. And then you get really disappointed when you realize you can't do that because computing won't let you do that. Well, that's an example of a many-body problem that can, in fact, be solved by quantum computers. Which is actually very interesting because now you go, oh, wow, that's basically predicting anything in the natural world. And so you need many quantum computers. Luke would be much happier if you could get him a bunch of quantum computers because then he could just simulate that atmosphere on Titan and we'd be doing much better. So drug interactions, weather predictions, how people develop, the differences between identical twins, stock markets, everything. You start getting these things that we think right now are completely unpredictable, impossible to predict. You could actually start predicting them. As I said back in 2023, optimization problems, particularly the kinds where the answer is of the form, how do I get to a good enough solution, not necessarily the optimal solution? And there's a lot of problems that fit that. So there are all sorts of interesting implications for network routing, solving problems, any kind of parallel problems like policy hardening. And of course, we talked about the NP problems like prime factorization. We'll get to that in a second. But the good news is a very recent Nature paper shows that many-body problems really can be solved with quantum. Very good. Okay? We've heard a bit about quantum cryptography. And I think boiling it all up into a takeaway, there's the quantum cryptocalypse, and that was a fun piece of art to find, which is, of course, that we're about to break the prime factorization that is the linchpin of RSA and other encryption. The big news is that this is sooner than most of y'all think. And I kind of tend to buy this. The US Office of Management and Budget is coming up with a prediction, which I'm going, the Office of Management, OMB is, okay? But they have this prediction. They're saying that we collectively need to start preparing, and the US government certainly needs to start preparing, because this is going to happen sometime in the next, since 2026 and 2030. That's a lot sooner than we've been hearing, but I can't remember who said yesterday, the pace of discovery and inventions has picked up enormously in the past 6 months. And that is true, and it's accelerating. So we're getting that second derivative effect, which is happening entirely in the background with all the fluff about AI, but this stuff is happening. So the OMB actually came out with a really good set of recommendations. I was kind of like, wow, this is great. It's intelligible, it's useful. I would encourage you to go read it. I think the links are in the book that you have. But what they recommend is, first of all, survey everything you've got, figure out where you're using cryptography, conventional cryptography, figure out what's vulnerable, what's at risk, and also layer onto it, hey, am I in control of this or is a vendor in control of this? Once you've got that, you've now analyzed everything, you can say, okay, fine, what's my roadmap for getting there by 2026-ish, or on the early side, which may mean changing your own software, going after your vendors and thumping them on the head, et cetera, and putting in slowly replacing or augmenting, I should say, as we saw from yesterday, with quantum proof classical cryptography today. I will point out that NIST just issued 3 algorithms that are, I will say, purportedly quantum proof. The only reason I say this is because the last time they issued 2 algorithms that were quantum proof, the Swedes broke them in about 3 weeks. And somebody had asked the question, what about the combination of AI and quantum? And it turns out that's exactly what the Swedes used to do it. They had side channel, which they used AI in to do that. So as much as I love the good folks at NIST and the good folks at IBM who came up with these algorithms, I'm just not holding my breath that they are as solid as claimed, but I sure hope they are. Okay. And then we heard a lot about quantum key distribution, so I'm super happy that this is the only slide that you're going to see, which is the use of quantum entanglement to distribute classical keys for classical cryptography. What it is not, quantum cryptography. And this is my point. When we all talk about quantum cryptography in the quantum cryptography market, we're not talking about quantum cryptography. We're talking about using quantum entanglement to distribute conventional keys. We're talking about the ability of quantum computing to break conventional cryptography. There are, in fact, algorithms, and we heard some of them yesterday, that actually exist that really are quantum cryptography, but they're not real yet in the sense that nobody's really making quantum cryptography products. So I suspect when we do the technology area benchmark, it's going to be mostly about research that's happening and not about companies, because quantum cryptography doesn't really exist as a market, which is kind of an important thing, because if you go and Google it, you'll find pages and pages and pages of stuff about it, but it's not really about quantum cryptography. So that's all we have to say about that. Quantum networking, this is kind of fun, and Jim asked me a very embarrassing, Ron was asking me a very embarrassing question, which is exactly the latency for this, and I don't remember above and beyond the speed of light, but basically you can use quantum entangled photons to transmit information, which is actually kind of cool. Now, if the information that you're transmitting is keys, then we're at key distribution, but you can transmit information that isn't keys, and that is quantum networking. All sorts of interesting reasons to do that. The big one is, of course, security. So if you happen to be in the military or military adjacent or an FFRDC, which means that's about half the people in this room, it's actually quite interesting, which is why Boeing, I kept wanting to say this, but Boeing has just sent up some satellites, or is actually planning to send up satellites in 2026 that will include quantum entanglement. So hopefully that's a win for Boeing, because they kind of need it. That is a nice little picture that I stole from the guys at Aliro Quantum, which is one of these sort of premier quantum networking companies. They have a network in place in, I think I mistakenly said a different city, but it's actually, I think, Chattanooga. And that it's in place, it's operational, you can go have a look at it. It is weirdly the power company that is also operating a telco network in Chattanooga. I'm not sure why, I haven't been there to visit yet. Very interestingly, about a week before this conference, there was a report by the National Quantum Initiative Advisory Committee, which is a pretty interesting sounding organization, with a strong assist from the good folks at IDA, talking about quantum networking and adjacent capabilities, including orchestration and management. There's a handful of them: Aliro, Qubitek, QConnect. Some of the research labs have test beds and networks. Again, this is for quantum networking, not any of the other forms. And it was EPB in Chattanooga, and I mentioned the Boeing satellites. And basically, the TLDR of the whole report is, hey, we need more money for test beds. We should invest more money in test beds. I don't have any issues with that, but it's not all that different from most government reports on most things.
Question down front.
Yeah, sure.
Could you comment about what's happening outside the USA in China or Europe?
Well, we actually included organizations outside the US in the benchmark. So,
Okay.
yeah, and as I said, the big thing that we're seeing as we talked about the Chinese network of satellites, that they're ahead of Boeing in their quantum entanglement, and that they are funding, they being generically anyone who's non-US, are funding more at a government level. So when you go through and you look at these organizations and you see what they're plowing into different shades of quantum, it's usually coming from the government. The Germans are doing a hell of a job, the French are doing a hell of a job, and so are the Chinese and a few other places. They're just pouring money. The Canadians are actually doing really well. There's hotbeds of quantum in Canada. So we're kind of at a disadvantage because we're relying on people with very short time horizons for benefits to come back. So, okay, current challenges. We just learned this. Speaking of breakthroughs happening, this is, I believe, this report I think it came out in April, but it got widely publicized in August. The fun thing there, okay, first, quantum entanglement vanishes above a certain temperature. It doesn't just degrade to hard to detect, it goes away. What's cool about this is if you guys haven't been following this space, the people that discovered it were a bunch of computer scientists who are not quantum engineers, who were trying to prove something entirely different, and they ended up showing the thing that they showed, but they got scooped by like 5 days by a bunch of actual quantum physicists. So they were kind of disappointed, but they said, hey, you guys have been looking at the same stuff, could you come and look at our stuff? And the quantum physicists discovered that in one of the steps of their proof, they had this incredibly important proof that was incredibly important for physics, which highlights something that sort of is what Dave was kind of touching on a little bit. And for those of you who remember Feynman and Feynman's books, one of Feynman's main points was always that he could develop and discover more things because he was cross-pollinated by lots of different fields. And I think one of the cool things and one of the real benefits of quantum generally is you've got engineers and scientists and theoreticians and experimentalists all working on the same stuff and cross-pollinating and cross-fertilizing wonderfully. I would say the biggest challenge with quantum networking is nobody really knows what it is, and they tend to confuse it very quickly with quantum key distribution, which is a subset of quantum networking. An important subset, it's a use case though. And so that frustrates me. So, we need to sort of get clearer on what we're talking about. Quantum sensing. Okay, and thank you very much to the clients who said, please look at quantum sensing because we think it's important, because they are right. Oh, shoot. There we go. What is it? It's basically photonic or solid state systems that capture high precision measurements at the quantum level. So it has nothing really to do with anything we've been talking about. No qubits are involved. It's just picking up information. But applications include extracting extremely small signals from noisy backgrounds. I don't know who might want to be doing that. And what examples there might be. Monitoring all sorts of forms of processes, particularly in hostile environments. Doing all kinds of really interesting imaging. We saw a lot of that happening in the labs on Tuesday. And then navigation replacing GPS. Why is replacing GPS a good idea? Because GPS could go away in one of a number of scenarios, including but not limited to global nuclear war, also just a random EMT coming in through nature. Yeah, exactly. Space weather, like all of us who are so reliant on GPS, like every morning I think to myself, and if this goes away, I am so screwed. So I'm very happy about the navigation. I could spend a ton of time talking about quantum sensing. As I said, the next tab is going to be on quantum sensing. If you have questions about it, you're curious, you think it's interesting, ask us because it's an area that we're very interested in. But I want to give you an existential reason why I think it's important, and it's tied to some of the previous presentations, particularly Kay's presentation on context. I'll talk about that in just a second. What's going on? McKinsey has this sort of very weird template, if you go look up their reports, where they basically have all the report written, and then they just search and replace sensing and networking, and then just change the wording where it needs to. But basically they say, okay, the ecosystem is applications and services, hardware and components, and essentially applications and services are getting mostly the majority, but really, it's pretty much a third of the investment that they're seeing. Okay, now we get into the fun stuff. I have what I will admit is an unproven thesis, but I'm holding to it until you disprove it, which is this. We heard Aaron talk about how telling stories is intrinsically human. It is like the human thing. It's also the case that humans, part of what you need to tell stories is to create categories, to create meaningful categories that are informed by your experience with the physical world. So that second bullet item, there is a fantastic and fantastically interesting book called Fire, Women, and Dangerous Things. The title, everybody loves the title, because if you're a woman, you're like, yeah, I'm kind of fiery and dangerous. Yeah, that's me. And everybody else is like, yeah, women are dangerous. But it turns out that it actually has to do with Aboriginal language. One of the Aboriginal languages has 4 categories of things. Just everything in the world falls into 4 categories. This is category number 2. Category number 1 is men, water, certain animals that are perceived as non-dangerous, and certain animals that are actually dangerous. Category 2 is fire, women, and dangerous things, and other, there's a long list. And then there's 2 more, which I don't remember at the moment. The thing that's interesting is when you first look at this, you say to yourself, that makes no sense. How did they come up with these? They're totally arbitrary. And the more you think about it, the more you realize it actually makes sense. And we could spend the entire talk on this, but we're not gonna. But it actually makes sense, and it makes sense because it has to do with how people experience the physical world around them. And what's the proof of how interesting it is those categories work absolutely brilliantly in modern, you know, they've just been able to seamlessly slot in every modern development. They know which category to put an automobile into and a spaceship and everything else. They can just slot it in. And if you think about it, it's kind of the same thing as gendered nouns in most languages. Like, why does a noun have a gender? And you, like in Russian, for example, there is a male form of mist and a female form of mist. But you know what they mean. When you look there, you're like, that's very female and that's not. And you could just see it, and you can't quite explain it, but it's your experience with the mist that causes you to do this. So effective categories have to be based on feedback from the real world. Then the last point, I was delighted that Dinesh taught me a term that I had known from neuroscience, and I knew that it was true since the 60s, which is, was it embodiment, but it's embodiment consciousness. That's cognition, thank you. I was trying to remember, embodiment cognition, which is that your brain, basically it's no brain in a vat, ever. It does not work. And this was like a thought experiment for neuroscientists until the 60s, until those experiments came out. And they realized the question is, if we took your brain and put it in a vat, and that was a science fiction, really fun science fiction series called Lex. And the predecessors, because it was Canadian, so they were predecessors, they had brains in vats that would occasionally speak up and weigh in on what was going on. That can't work because the intelligence would be destroyed because there's so much intelligence embodied in your physical body. Well, hang on then. What does that actually mean for AI? And here we come to my thesis, which is this, which is AI will never become AGI until it gets feedback from categories that are informed by the physical world. I don't mean it needs necessarily feedback from the physical world, although that's possible, but it can't create meaningful categories until those categories are informed by the experience with the physical world. To get to AD, yes! And Kay is going, it's context. I'm going, yes. That's why we were like doing the whole eye contact thing the whole time you were talking. And if that's true, then the missing link is quantum sensing. Because now you give AI the ability to pick up information in all sorts of different ways, in non-deterministic ways that map exactly to, not exactly, but broadly to how we experience the world, which is non-deterministic and all those other things. And then what that means is you might have quantum applications in analytics plus AI, and you get this feedback loop based on quantum sensing. And in fact, if you recall from the field trip, the thing that blew my mind, I was standing in the back of one of the displays and they were talking about, oh yeah, so basically we're just picking up the phase change. Now, nothing, like we know that we can see frequency and amplitude, but we can't see phase change. And no living creature that we know of sees phase change. Quantum sensors can pick up phase change, so now you have the ability to inform an intelligence that becomes entirely alien because they have senses we can't even imagine. Okay, now you're going to turn this into that. So my thesis is AI plus quantum sensing could equal AGI. And that's it. Thank you. I love it. You are welcome to ask questions, but I think we're over time.
No, we have 4 minutes left.
Okay. So, okay, everybody really wants to get to lunch, I can see.
Okay.
Well, you know you can grab me at lunch. You know how to reach me, so see you at lunch.
Actually, Johna,
Oh, yes, Mercedes.
I think we both have a question here. We're sharing the same mic. I'm going to go first. And I probably should have interrupted you when you were talking about quantum safe cryptography. I just wanted to clarify something you said about QKD. You said it was algorithms and classical algorithms anyway, and I just want to understand that because that's not how I understand it.
Yeah, because the keys that you're sending are actually, in many cases, you're just transferring classical keys.
Classical keys, but no, there's no algorithm attached to it.
Yeah, exactly.
Okay, great.
It's key district algorithms, right?
Sorry, what?
By classical encryption algorithms.
Exactly.
Classical keys for classical algorithms being transmitted non-classically using
That's
quantum
what
channel.
John just said.
Okay.
Yes.
Over lunch.
The quantum is, so basically the quantum modifies the distribution, not the key.
But the algorithm is for the distribution.
No, actually no, the algorithm is for what you do with the key when you get it.
There is an algorithm
yeah.
for distribution as well, but
but-
it's separate from the encryption
yeah.
activity.
Yeah.
Back in 2011, when I was challenged with, take a look at this thing called quantum sensing, one of the things that came up is apparently the European robin has a chromophore, in other words, a special protein that detects light and color and so forth, but it's actually activated a special part of the molecule in there that apparently holds quantum entangled coherence long enough to actually be useful for detecting magnetic fields. And they're trying to re-engineer that back into something useful for things where you need to be able to detect magnetic fields of some sort or disturbances in magnetic fields for obvious reasons. But it was fascinating that they discovered that at the temperature of the body of the European robin, it is possible to maintain some level of quantum coherence, whereas a lot of other technologies that we've come up with require supercooling.
That is fascinating. I don't understand why they can do that at like body temperature of robin when they've sort of just proven that entanglement disappears. So that would be something interesting to dig into, but still the fact that
Excuse me, entanglement often disappears, but you can build real things that are entangled at large scale in stable ways that exist at room temperature.
And I was trying to read it fast, but the literature is at high temperature. I was trying to figure out
yeah, there is
exactly
a
where the
temperature,
height-
that's true. It
right,
doesn't have to
where
be
the height is.
cryogenic. So that's an, yeah, there
Okay,
is a temperature.
I'm sorry,
Excellent
folks.
point.
I got Terry lined up, and then if we have time, we'll take a couple more.
Real quickly,
No.
comment about entanglement disappears at a certain
At
temperature.
a temperature, you're right.
But-
I didn't think about how high the temperature was. It's just,
My question is, have they explored why?
I think so, but I'm not sure I understand the article enough. There is a link in the book so that you're welcome to have a look at it. You will now be where I am in terms of understanding it because it just came out. And I think the actual temperature also varies. I don't think it's a fixed temperature level. And so the real question is, what does it vary based on? But the fact that mathematically it just stops after a certain point is still interesting. Yeah, Nancy.
It depends on what the system is and the Hamiltonian that's governing it. So,
Yeah.
you know, that's what determines what the temperature is, because it's relative to the system in question.
Okay, last word, Jim.
So we actually have some of our first papers just accepted, and we've found something that was not previously kind of predicted in quantum computing, nor can we demonstrate it robustly, which of course we have lots of people trying to do now. We found that for some very standard algorithms, mostly machine learning algorithms,
course you would.
SVMs versus quantum SVMs and things like that, that we actually get very different ROC curves, very different. So So when the quantum computer says X is true, it's significantly more often right than the
So
traditional
quantum
algorithm.
enhanced ML.
But when it says something's not, it misses a lot. So interestingly, we're seeing that even for standard computation,
That's a first.
we're starting to see some interesting impacts. And again, with only
Yeah.
120, well, we have 140 qubits, but then you have to make them into
Non-noise and or correcting
anyway.
it. Yeah.
But suffice to say, even with a very small amount of computing, we're beginning to see that actual traditional algorithmic, well-understood stuff seem to behave differently.
Which is really cool because
Yeah.
because basically the sort of loose assumption until now has been there's stuff that classical will always do better and stuff that quantum might do better, and the idea that we could improve on classical in any way
Well, or that
not always
combination
improve.
may be able to do things that neither can do.
Exactly.
That's
yeah.
really
All right, and we are well over, so
We will wrap it up at this point. Jonah, thanks so much.
Oh,
really.
thanks.